Previously, we mentioned that if the characteristic of the field K is not equal to P, then the pth cohomological dimension of K is going to tell us a few things about the Browne group, the norm group of extensions of K. However, when the characteristic of K is equal to P, then we already know that the pth cohomological dimension of K is going to be less than or equal to 1, so this condition doesn't imply anything special. So let's prove this. So recall, by definition, this is just the pth cohomological dimension of the absolute Galois group of K, right? And so that from before, we know that this is going to be equal to the pth cohomological dimension of its P pro P CeLO subgroup. Why do we want to pass through this? It's because for pro P group, remember, to prove this, it suffices to check the cohomology only in 1 degree, right? And with coefficient only in Z mod PZ. So in general, we always want to pass through the pro P CeLO group, and then we can just check cohomology in 1 degree and in the coefficient Z mod PZ only instead of any continuous torsion G module. So without loss of generality, we might as well assume that this group G was pro P to begin with. So we want to show that this cohomology group vanished. This is just Galois cohomology, so I'll use the usual notation. And to do so, as usual, we will want to look at the long exact sequence of cohomology associated to some short exact sequence. Here we want to look at the short exact sequence in the proof of Artin-Schreier. This is the characteristic P analog, or we can say the additive version of Kummer theory. So part of the sequence will be this. Here is the group we're interested in. Now the claim is that these groups vanishes, they are 0. So then this would mean that our group must vanish. Okay, so it remains to show that these groups are 0. And this is actually a statement that was used in the proof of the cohomological version of Artin-Schreier. It suffices to prove the vanishing of the Galois cohomology for finite extension instead, because this cohomology group is just a direct limit of these cohomology groups. So let L over K be a finite extension, finite Galois extension. We want to show that the following Galois cohomology vanishes for I greater than 0. The key idea here is to view L as the co-induced module of K. And this allows us to use Shapiro's lemma to pass through this cohomology of the trivial subgroup, which is 0. So why is L equals to the co-induced module of K? This is by the normal basis theorem. It says that if L over K is a finite Galois extension, so let's say the Galois group is given by this, then there must exist an element alpha in L such that sigma 1 alpha, sigma 2 alpha, and so on, sigma m alpha, these gives a basis of L over K as a vector space. But then we see then that this gives an isomorphism between these as K vector spaces. Now as a Galois module, this is isomorphic to the co-induced module by the following lemma. So how do we get this isomorphism? Well, every map F in here is uniquely determined by the image of the sigma I, where the sigma I here are the elements of the Galois group because they generate this as a Z module. So F should correspond to an element that captures all of that information. Conversely, if we want to think in terms of tensor, then each of these simple tensor map to map F such that F sigma I is equal to this A and F sigma J is 0. Thus, we have an identification of L with a co-induced module of K by passing through this. By Shapiro's lemma, this shows us that this cohomology group is 0, and thus originally these cohomology group are 0. So patched together these cohomology group, we get the Galois cohomology group. This is of the absolute Galois group of K. It vanishes for I greater than 0. Putting it back here in this long exact sequence associated to this Artin-Schreier short exact sequence, we get that this H2 group should be 0. Since we are assuming that the Galois group is a pro-p group, this means that the codimension, the pth cohomological dimension of the Galois group is less than or equal to 1, as claimed.